Please welcome, from Texas A&M University, Dr. Matthew Sheldon.
Afternoon, and thank you very much for your attention today. I'm going to speak very briefly about my lab's research in non-equilibrium nanophotonics and hopefully try to convey how this is relevant in defense. Now, right off the bat, I understand that the term non-equilibrium nanophotonics is a bit of a mouthful, kind of some jargon. So what do I really mean? The basic idea, or the main point of my talk I'm going to try to get across, is the power, the capabilities, and the increases in what we can do with radiation by fundamentally controlling its interaction at the nanoscale. And the nanoscale is very small. It's when we're talking about optical structures that are on the order of tens or hundreds of times larger than the atoms that actually comprise the optical structure we're interested in. So first off, right off the bat, what is photonics? How is this interesting or relevant in defense? So photonics describes the research in technology, or the development of technology for the generation, detection, and manipulation of electromagnetic radiation. I think a lot of people immediately have some intuition of how this is relevant in your daily life and in broader contexts. For example, communications is built on photonics technology, whether we're talking about fiber optics or if we're talking about the wireless communication that makes modern lifestyle possible, right? Spectroscopy is also a photonic technology, which is basically the analysis of the frequency distribution in radiation signals. And this underlies things like sensing, detection, and monitoring. As an example on this slide, I have someone using night vision goggles. This is based on detecting infrared or thermal radiation and transducing it into a signal that we can see with our own eyes. These things are underlined by our ability to control electromagnetic radiation. And when we think about what limits how well we can do this now and the types of technologies or applications we might want moving forward, it's going to come down to how much better we can control this fundamental interaction. So for example, we think about embedded environmental monitoring with sensors that are wirelessly connected that scavenge power locally. All of this can be enabled by better control of photonics. So what's special about nanophotonics, or why do we care about nano? Well, basically, everything up till now that we've developed technologically is fundamentally determined by the interaction of phenomenon on the wavelength scale of radiation. And when we go to the nanoscale, things are fundamentally different. The rules of the game are changed. Basically, I have depicted on this slide a schematic of a sort of prototypical example now in the field of nanophotonics, which is a metal nanoparticle. When the metal nanoparticle is smaller than the wavelength of radiation, all of the electrons, all of the free carriers in the material can respond instantaneously to the oscillating field of the driving radiation. This is fundamentally different from what's limited or defined our capabilities in conventional photonics up till now. This gives greater concentration of energy. It allows you to transduce more quickly at different frequencies and speeds, sort of fundamentally rewriting what you can do. As an example on this slide on the right, I have an image of when you change the size or the shape of these nanoparticles, how it changes their interaction with light. The colors are very pretty. That's interesting, okay? But this is also enables a kind of capability if we structure space, taking advantage of these same sort of fine level sub-wavelength nanoscale control. You can do something that really seems like magic, which is like an invisibility cloak. Maybe you've heard this science headline. This was one of the first demonstrations of how you can leverage these nanophotonic effects to do something like make a region of space that can't be detected, is truly invisible. Okay. But what my research laboratory focuses on is trying to understand, well, if all the rules are changed, what still limits us? What's fundamentally what we're up against? And we think about this problem in terms of thermodynamics of radiation. Sort of to get to the punchline of the story, my laboratory analyzes the sort of non-equilibrium behavior of radiation by analogy to the way that the original steam engines were analyzed and developed the modern laws of thermodynamics. We basically think of the radiation field of light itself as the working fluid, or the steam in sort of broad classes of heat engines that leverage these photonic or radiative interactions. And our skill sets are in the physical chemistry, the optical physics, the modeling, the materials development, and the fabrication of these types of materials. Now, in my last slide here, I can't tell you about everything in my laboratory or all the things that might be of interest or relevance here. Hopefully, there's a keyword or something that might grab your attention. And I'll just leave with one little vignette, which is the top left of this slide. We've developed some optical platforms that get cold when you shine light on them. And this fundamentally changes how they interact with radiation, how you might do thermal cloaking, the limits on energy conversion and power transduction that they achieve for you. So thank you for your attention, everyone.